Welcome to this scientific lecture on programmable microcapsules. Today we will explore sophisticated multi-shell systems that respond selectively to stimuli such as pH, enzymes, and temperature. Let us begin by defining what microcapsules are and why they are important in modern materials, science, and pharmaceutics. Microcapsules are spherical particles with a core shell architecture. The core contains the active substance, while one or more shells provide protective barriers and control release kinetics. These structures typically range from 1 to 1,000 micrometers in diameter, placing them in the colloidal and microscopic regime. Here we see a schematic representation of a multi-shell microcapsule. The innermost yellow region represents the active core material. Surrounding it are multiple shells, each with distinct chemical and mechanical properties. Applications of programmable microcapsules span pharmaceuticals for drug delivery, agriculture for controlled fertilizer release, and advanced materials for self-healing and sensing. Now let us examine the design principles behind multi-shell microcapsule systems. Why do we need multiple shells? An important question arises: why use multiple shells instead of a single protective barrier? The answer lies in sequential stimuli response. Multiple shells allow us to program the capsule to respond to different environmental triggers in a specific order, creating sophisticated release profiles. Each shell can be engineered to respond to different stimuli independently. For example, the outer shell might respond to pH, while an inner shell responds to enzymatic degradation. Different shell materials respond to distinct environmental triggers. We can combine pH-responsive polymers, enzyme-degradable peptide linkers, and temperature-sensitive hydrogels to create programmable release cascades. Let us now discuss the chemistry and physics of stimulus-responsive shell materials in detail. pH-responsive polymers are perhaps the most widely used in controlled release systems. These polymers contain ionizable functional groups that protonate or deprotonate, depending on the environmental pH. This causes swelling, dissolution, or structural changes. The degree of ionization alpha equals 1 divided by 1 plus 10 to the power of pKa minus pH. This Henderson-Hasselbalch relationship governs the ionization state. Common examples include polyacrylic acid, which is anionic, chitosan, which is cationic, and commercial Udrigit polymers designed for enteric coating. This graph shows the degree of ionization as a function of pH for two different polymers with pKa values of 4.5 and 6.5. Notice the sigmoid transition around the pKa value. Enzyme-responsive shells offer exquisite biological specificity. These shells incorporate specific peptide sequences, or ester bonds, that are cleaved by target enzymes such as proteases, esterases, or phosphatases. The degradation rate follows Michaelis-Menten enzyme kinetics, providing a well-understood framework for predicting release rates. The reaction velocity equals Vmax times substrate concentration divided by Km plus substrate concentration. This describes how quickly the enzyme degrades the shell. Temperature-responsive polymers undergo phase transitions at specific temperatures. Many exhibit lower critical solution temperature, or LCST transitions. Below the LCST, the polymer is soluble and swollen. Above it, the polymer collapses and becomes hydrophobic. A classic example is poly-N-isopropyl acrylamide with an LCST around 32 degrees Celsius, close to human body temperature. Now let us examine the fundamental transport process, diffusion through capsule shells. An important question arises: how does the size of the drug or active molecule affect its diffusion rate through the shell? The answer comes from the Stokes-Einstein equation. The diffusion coefficient is inversely proportional to the molecular radius. D equals Boltzmann constant times temperature divided by 6 pi eta r, where eta is viscosity and r is molecular radius. This means larger molecules diffuse significantly more slowly through polymer matrices, allowing size-selective release. This graph illustrates cumulative release profiles for molecules of different sizes. Small molecules in red are released rapidly, while large molecules in green show sustained slow release over many hours. The mathematical description of diffusion through spherical shells follows Fickian transport theory. The general diffusion equation in spherical coordinates provides the foundation. Partial C by partial T equals D divided by R squared times partial by partial R of R squared times partial C by partial R. This describes concentration evolution with time. Boundary conditions at the shell interfaces depend on partition coefficients, shell permeability, and external sink conditions. For shells undergoing degradation, the effective diffusion coefficient increases with time as pores form and grow. D effective of T equals D0 times 1 plus beta T to the power n, where beta and n are empirical parameters describing pore evolution. For complex multi-shell systems with multiple stimuli, analytical solutions are not available and numerical methods such as finite element analysis are required. Let us briefly discuss experimental techniques for characterizing microcapsule properties and release kinetics. Scanning electron microscopy, transmission electron microscopy, and confocal microscopy provide detailed structural information about shell thickness and morphology. Dynamic light scattering measures size distribution and can detect swelling behavior in response to environmental changes. UV-vis spectroscopy and fluorescence spectroscopy track release kinetics by measuring active agent concentration in the surrounding medium over time. Atomic force microscopy and micromanipulation techniques measure shell mechanical properties, including elastic modulus and rupture force. Finally, let us explore some advanced design strategies for next-generation programmable capsules. Layer-by-layer assembly techniques allow precise control over shell composition and thickness at the nanometer scale by sequential adsorption of oppositely charged polyelectrolytes. Microfluidic devices enable production of highly monodispersed capsules with precise size control and complex internal architectures. By combining multiple stimuli-responsive materials, we can create capsules that act as Boolean logic gates, releasing only when specific combinations of conditions are met. This schematic shows a Boolean and gate capsule. Release occurs only when both pH stimulus in red and enzyme stimulus in blue are present simultaneously. This provides exquisite control over release, location, and timing. Feedback-responsive systems can be designed where initial release triggers further release, creating autocatalytic or self-amplifying behavior useful for rapid response applications. Let us consider an important, practical question. What are the main challenges in translating these sophisticated capsule systems to clinical or commercial use? The answer involves three major challenges: scalable manufacturing to produce billions of uniform capsules, reproducible performance across batches, and navigating complex regulatory approval pathways. Additionally, all materials must demonstrate biocompatibility and ideally biodegradability to avoid accumulation in tissues or the environment. Let me summarize the key concepts we have covered in this lecture. Multi-shell microcapsule architectures enable sophisticated programmable release profiles by combining selective response to pH, enzymes, and temperature. Successful design requires integrating Fickian diffusion theory, shell mechanics, and degradation kinetics into a unified framework. Applications span diverse fields including targeted drug delivery, controlled fertilizer release, and autonomous self-healing materials. Advanced fabrication techniques such as layer-by-layer assembly and microfluidics enable capsules with complex logic functions and feedback mechanisms. Future directions include truly smart capsules that incorporate sensing elements and computational capabilities to make autonomous release decisions based on real-time environmental monitoring.